Okay, so I have uploaded the assignment. Okay, so try to do it as you can, no problem, no worries. Okay, because that assignment will be somewhat difficult. Okay, it is not the easy one. Okay, so I hope maybe so you can answer these questions definitely. Okay, so please check my video also. Okay, so if I haven't cover any of this parameter, you can ask me. Okay, then I can again do that one. So anyway, I have already uploaded the notes. No, so in the notes also these are available, these parameters are available. So if you have any problem, you can ask me. Otherwise, maybe there are a lot of sources there. Okay, so if you want to if you couldn't understand any of these, you can directly ask me, no problem. Okay, so I think this one you can do. Okay, you can do. So try to do it. At least this 1 and 2 questions. Okay, and maybe this one also. I hope you can do it. Okay, so maybe when you are doing this one, when you are going to do this one somewhat difficult. Okay, because you can see that here we have given antenna current distribution. So current distribution is somewhat complex. Uh, Complex means it is complicated. Current distribution is complicated actually. Okay. So if the current distribution is complicated, okay, we know that um, when we are calculating the stuff, okay, when we are calculating the stuff, okay, so it is like this, okay. Okay, so it is like this, okay. So the current distribution is given, okay. This is the current distribution, okay. So the current distribution is given, okay. So first you have to find the magnetic vector potential using this equation. We have derived this, okay. So this is the current distribution for line current, okay. So instead of this current distribution, you have to use this one, okay, in the Z direction, okay. So you have to do the integration, okay. So once you evaluate it, you can get the result for the magnetic vector potential. So it is very hard maybe, okay. So maybe the integration will be much difficult because there is a cos square terms also there, okay. And maybe come to this kind of compact solution may be hard, okay. So anyway, you can find the magnetic vector potential, okay. So try to find it as much as possible. No need to go to a very simplified version, okay. So if you can do it, if you can't evaluate this integration, also I am okay with that, okay. So try to maybe for your knowledge, you can ask a mathematics teacher or someone to do for that integration maybe, okay. That is good for you, that is good for your knowledge, okay. So then you can derive this H field and E field using the vector magnetic vector potential A, okay. Then we can derive the average power density, okay. And then we can derive the total radiated power, so on we can derive the things, okay, derive the stuff, okay. So first thing is you need to apply this current distribution and find the magnetic vector potential. So that integration may be hard, okay. So I'm not expecting these kind of simplification from you, okay. But I want to show you how we can use mathematics to solve complex problem in engineering, okay. So that is my only target, okay. Okay, so try to do this as much as possible as you can, okay. So submit it, then I will submit. So try to do this question, okay, up to this one, this up to 5. Definitely you should be able to do this up to here, okay. So so I will give you the marks based on the submission. Okay, don't worry about that. Okay, okay. So now I think we have almost covered the LO1. Okay, learning outcome one. Okay, actually some more parameters also we have learned. Okay, so in LO1, okay, we have to learn the type of antenna we have already discussed. Okay, and radiation pattern, radiation power density. Okay, radiation intensity. So we have covered uh, these parameters. Okay, and infinite small dipole we have discussed. Okay, and so I have uploaded the lectures. Okay, in uploaded lectures I have discussed about this infinite small dipole. Okay, and we see how to derive the magnetic vector potential, radiated, sorry, average power density, then total radiated power. Those we have derived for infinite small dipole. Okay, because for infinite small dipole means it is very small antenna. The length of the dipole is less than lambda divided by 50. Okay, lambda divided by 100 or something. Okay, so it is very small. Okay, due to it is very small, the current distribution is uniform. The same currents are there along the antenna. The current is same, I. Okay, so the integration will be very easy here. Okay, so we have derived the parameters related with infinite small antenna. Okay, and small dipole antenna is another type. Okay, and so here the length, this also categorize using the length. මේ length එකෙන් තමයි මේක infinite small the small dipole එහෙම කියලා මේවා කරලා තියෙන්නේ. එතකොට මේ infinite small කියන්නේ ගොඩාක් පොඩි ඒවා. හරි? So I will show you. Okay. That is for cover the L. Okay. So infinite small antenna. Infinite finite small dipole. Okay. Okay. The dipole length is very far less than the wavelength. This infinite dipole. ඒ කියන්නේ wavelength එකට වඩා ගොඩක් අඩුයි යාගේ length එක. යාගේ design frequency එක yeah, this is okay. Lambda is okay. The the give me a moment. Okay, dipole means we have two poles. Okay, one pole is like this. And there is another pole. So these are conductor. Okay, so this is a dipole antenna because there are two sticks, two poles. Okay, so that is why it is called dipole, and we have like this. This kind of is a dipole antenna, And if you get the length here, length is L, okay. And if you want to design the antenna for some frequency, F, okay. So wavelength can be calculated using V equal F lambda, okay. V, you know, that is 3 into 10, 8 or something, okay. And it should be divided by F, that is the lambda, okay. So you have a value for lambda for a design frequency, okay. So if you select the length, okay, if you select this length very less than lambda divided by 50, that means very small length, okay. So this is called infinitely small antenna. This infinitely small dipole antenna. This is infinitely small dipole, okay. So, so because this is very small, the current distribution along this antenna is uniform. That means the current along this antenna is uniform, that is I, okay. So the current distribution is very simple, okay. So you can easily derive the things, okay. The magnetic vector potential, you then E field, H field, okay. Then average power density, total radiated power, so on you can derive, okay, because this is easy, okay. And small antenna means, small dipole means the length this is small, okay, or short dipole. Actually, this is the small dipole, okay. That means length, the antenna length, okay, is less than lambda by 10 and greater than lambda by 50, okay. If a dipole is designed with this range, with this length range, the length should be greater than lambda over 50 and less than lambda over 10. So we called it small dipole, small dipole. So this dipole is somewhat bigger than this one, okay. So here the current distribution is not uniform, okay. So I will give you the current distribution. Maybe for a note I have uploaded the note, okay. So in that note I have mentioned the current distribution for the small dipole antenna, okay. So actually if you have the idea what is a small dipole antenna, that is enough, okay. You no need to remember the current distributions, okay. Current distributions of any antenna, okay. So if needed, we can give, okay. It will be given to you, okay. Okay. And finite length means, okay, finite length antenna means lambda that is greater than the length of the antenna, okay, length of the antenna is greater than lambda divided by 10, okay. So this is called finite length antenna, finite length antenna, okay. Finite length dipole antenna, okay, if the length is greater than lambda divided by 10, okay. And very popular finite length dipole is, what is that? That is half wave dipole, okay, half wave dipole. We called it half wave dipole, okay. And we connect, we select L is equal to lambda divided by 2, okay. So the L is equal to lambda divided by 2. This cell antenna length is equal to lambda divided by 2, and this is we called half wave dipole, okay. And here also the current distribution is very complex, so it is somewhat hard to derive this, okay. So this is not mentioned here, okay. So as I can remember, I could remember this as a half wave dipole, but it is not a half wave dipole. It is not given, okay. This also finite length dipole here. This example is also finite length dipole antenna, okay. So these are the three types of antenna, okay. Three type of dipole antenna, dipole antenna, dipole antenna. One is infinitely small. That means the antenna length is less than lambda. over 50. Then small dipole, that is the length is greater than lambda 50 but less than lambda 10. Then finite length antenna, finite length, that is lambda, sorry, L is less than, sorry, L greater than lambda divided by 10. These are finite decimal. Okay. So one example is lambda by 2 half wave dipole. Okay. So these are the basic three types of dipole antenna. Okay. So, so these are the finite dipole antenna. Okay. And the array antenna, we have in my lecture, I have just introduced what is the array antenna. That means uh, we are using uh, more than one radiation element for transmitting. Okay, so we call them array antenna. The array, using the array, we can send a signal to a specific direction. Okay, so I am hoping to do the phase array antenna. Okay, that is one type of array antenna, that is phase array. Okay. Okay. So these are called scanned array also, electronically scanned array also. Okay. And so you can see that, okay, so you can see that there are number of radiating element. This is a phase array. Okay. This is a phase array. There are number of radiating element. Okay. And each element are fed with the signal. Okay. Fed with the signal, but different delay. You can see that this antenna is transmitting first. Okay, so first the signal is direct uh, the feed to this antenna. Then second, this antenna is feeding, transmitting. That means signal is fed to this antenna after that, secondly. Okay. Then again, this antenna is again has a delay. Okay. This one delay. Okay. So you can see that when we are when we are delaying the antenna, when we are delaying these signals, okay. So the so you can see that this antenna is radiating in this direction. This also radiation in this direction. But all together, so you can see that the the radiation is phased to this direction due to this delay. Okay. So using this delay or phase shift, actually delay means a phase shift for a signal. Okay. If you so phase shifters are also there. Okay. And if you just make a delay to feed the signal to this each antenna, then you can uh, change the direction of this radiation field. Okay, we called it beam. It is called beam steering. Okay, beam steering. Okay, and also beam forming. Okay. So we can beamform the antenna. That means we can send the signal desired direction. Okay. So you can see that when we are changing this delay, so this theta will be changed like this. Okay. So that is what it is called scan array. Okay. Electrically scan array, because it can scan. It can the uh, send the signal to any direction. Okay, the direction can be changed using the delays. Okay, so so this is one advantage of a phase antenna, array antenna. Okay, so I hope to discuss. So here actually they are expecting only the idea. Okay, so but if we have time. Um, if we have time, we will see how we can how we can beamform using the array antenna. Okay. Uh, so electronically also, and maybe you can see that. Okay. So for example, I have closed, no. Yeah. So so you can see that. Okay. I will show you that. Okay. So you can see that. Okay. So if you are sending the signal here, okay, that means if you make this length, okay, this is the transmitter, this is the signal generator, and if you make this line, transmission line length, okay, let's say that this is L1, L2, L3, L4, L5, like this, okay. So if you make L1 is greater than L2, L2 is greater than L3, likewise. If you if you if you uh, short if you short the cable, or if you reduce the length of the cable, if you reduce the length of the transmission line, you can see that the signal will be fed to this antenna with a delay. Okay, so I hope you can understand, okay, what I'm saying. Okay, I'm saying that we have a transmitter here. We have our transmitter. It is a signal generator. Signal generator. Okay. Now we take signal generator and feed one antenna like this. Okay. Now we take the same signal here. Okay. And this is the antenna. Okay. This is the antenna. This is antenna. Okay. Now it is radiator. Okay. Now we take the signal and we just select the length of the cable, length of this transmission line. Okay. Let's say that length of this transmission line is L1, L2. This is L1. Okay. If I select L1 greater than L2, that means uh, the signal feed first. Okay. This signal from here to here, it it reach first. Okay. Then then for the second and this antenna, after that, after this signal, the the signal to this antenna will come here. Okay, that means it has a delay. Okay, that means you can change the delay by changing the length of the transmission, this feed line. Okay, this is the feed line to the antenna. Okay, this is we call the feed line because we use this cable. This may be a transmission line, maybe a coaxial line. Most probably it will be a coaxial line, coaxial cable. So if you make that cable length higher than this one, you can introduce a delay. Okay. So very easily, maybe you can do that beamform using the array. Okay. So I think that idea is enough. Okay. But if we have time, we will, sometime we use the antenna driver circuits to drive the signal to the antenna. Okay. So we can automatically beamform the signals. Okay. So I think so those we have to discuss in learning outcome one. Okay. So I think we have discussed the learning outcome one. Okay. But if we have time, we will try to develop or try to see what happened, how we can beamform. That means how we can change the radiation direction of the antenna using this array. Okay. So we will see it if we have time. Okay. Okay. Now we come to this part. Okay. That is LO2, learning outcome 2. Okay. So here we have to learn the antenna matching techniques. Okay. Antenna matching techniques. That is what we need to learn here. Okay. Uh, so as usual, I'm going to use Professor Disalu Duawala note. Okay. So here the most of important matching techniques are mentioned. Okay. So that is enough for our level, okay? And this, I will share this PPT, but I need to take the permission from him before sharing. So once I take the permission, I will share this to the LMS, and these are narrated, okay? Actually, you no need to listen to my lecture, okay? So if you can listen to this lecture, that will be very effective, okay? So I will upload this, and it is narrated, okay? So you can see that it is narrating, okay? Okay, you can see, okay? Okay, so it is narrated. You can click here, then you can, the explanation is there, okay? So I will upload the once I get the permission from him, okay? So you can refer them, okay? But I will tell what are the important things, okay? Important thing for us, okay? So we will start it, okay? So it is LO2, okay? Learning outcome to LO2. That is antenna matching. Antenna matching. Okay. So this is if you have any problem, you can ask, okay? So this is very interesting things, interesting subject, is interesting title, okay? Title. And you already know about matching, no? You have learned in microwave engineer, matching, okay? So anyone can tell why we need matching? Why we need matching? So currently, if we are using high-speed electronic circuits, okay, the matching is very essential part in those circuits. For example, if we consider our phone, okay, if we consider our phone, so you know that it has antenna, okay. Actually, our phone has a patch antenna, okay. 4 patch antenna are there in our phone, okay. So it also use a array, okay, in our phone, in our mobile phone. We use normally 4 patch antenna array. In semester exam will be open book, okay? It will be open book, okay? Don't worry, okay? And the marking criteria is, I think I have uploaded, no? Here, haven't I put it? Yeah, this continuous assessment 40 and final exam 60, okay? For continuous assessment, we have, it's not mentioned here. We have, we have we will have 3 assignment, okay? We will have 3 assignment, and actually the lab session also there, okay? We will try to do that lab session at least using HFSS, okay? Now you are in intern, okay? So maybe it may be hard to come to the campus, okay? So we will try to do the lab session using online, okay? So one lab session is there, okay, and mid exam, okay. The mid exam we will held on uh, not next week, after week, okay. After week we will held the exam, mid exam. Uh, I will upload. I will upload the paper. Then within 2 or 3 hours, you can write the. So that one also will be a online one, okay, the online exam, okay, and so you can upload the papers, okay, once you have written, okay. So, and final exam will be a physical exam. It is not an online exam, but it will be open. Okay. So that is how that is the marking criteria. Okay. Is that okay? Okay. Thank you. Okay. So we will move on. Okay. Okay. First, someone can tell me. Okay. So what I'm going to tell you is that, okay, in our phone, we have 4 patch antenna. Okay. We have 4 patch antenna. Okay. Actually, here using a phone, we are not doing any beamforming. Okay. Here we are not doing any beamforming. Okay. This 4 antenna is used. Can anyone tell why we use 4 antenna? Maybe in wireless communication system. Maybe you have learned this in communication systems. I think you have learned this. Okay. Why we use 4 antenna for our phone? Why we use 4 patch antenna for our phone to, to our phone? Actually, we are using MIMO technology now. This day we are using MIMO technology. Okay, MIMO means multiple input, multiple output. Okay, multiple input, multiple output. That means you have multiple transmitting antenna, and multiple receiving antenna, multiple receiving antenna. Okay, so this antenna will transmit and it will get here, this one here, this one here, like so. So in this way, you can get the same signal from many antenna. Okay, and then you can decode those signal in effective manner. Okay, so you can increase the signal quality using this technique. Okay, so I'm sure that you have learned these MIMO techniques in communication systems. Maybe I'm not sure. Okay. Um, so actually now we are using MIMO systems. Okay, currently we are using MIMO wireless system for communication. Okay, now actually we are using massive MIMO. Okay, uh, massive MIMO means there are around hundreds transmitting antenna and very high number of receiving antenna are used in massive MIMO, but not for all application. Okay, not for all application. Okay, but this MIMO is used for 4G, 3G, 2G, those technologies. Okay, and also for WiMAX, Wi-Fi. For that technologies also. I'm not sure about Wi-Fi. Okay, but for WiMAX, the MIMO systems are used. Okay, so okay, so we have the antenna array. Okay, and all signals are combined. Okay, combined or selected. Okay, then the one signal will be so anyway the received signal will be taken. Okay, so then maybe uh, the filter is there, like is filter maybe there, band pass filter, then amplifier. Okay, amplifier, then it goes to the demodulator. Okay, to decode the signal, decoder. Likewise we then maybe send to the speaker or something. Okay, so you can see that this kind of path is there. Okay, so you can see that the signal is uh, traveling from one component to another component, one component to another component. Okay, So why we need matching? Actually, signal is uh, is transfer is transferred from one section to another section. Okay. So for example, let's say that your signal is feed to a filter. Your signal is feed to a filter or amplifier. Okay. Then there is output filtered signal. Okay. So now your signal is fed to the filter, then you can get the output signal. Okay. So filtered signal here. Okay. So uh, so you know that, okay, this is a transmission line. This is a transmission line, TX line, transmission line. And this is a component. It is a filter component. Okay. So it may be a passive filter, digital filter, anything. Okay. So it has the input impedance. We have learned them though in microwave engineering. We have learned them. Okay. The two ports network parameters. Under two ports network parameters, we have learned them. Okay. The Z parameters, S parameters, so on. Okay, we have learned them. Okay. So anyway, this has a input impedance. Input impedance. Okay. In this input port has an impedance that is we called input impedance, and this output port also will have an impedance that is output impedance. Okay. Now you can see that signal, this impedance, the transmission line impedance will not equal to this component impedance. Okay. So when the signal is transferred to this component, so these two impedance are not matching. Okay. You have the signal, you have a transmission line like this, and here maybe there is another equipment or filter. Okay, filter. Okay. So this impedance, the transmission line impedance. Okay, transmission line impedance, that is the characteristic impedance. Okay, of the transmission line. Okay, then this impedance. So this is the equipment impedance. So this impedance also will have another we don't know, some input impedance. Okay, this equipment or component. Okay, so when the signal is transferred from this side to this side, due to this impedance unmatching, the signal will be reflected. Okay, so you have learned those things. Okay, the reflected signal can be that reflection can be defined, that is tau, that can be defined as this is the uh, this is the input impedance Z in minus ZC divided by Z in plus ZC. Okay. So this is the reflection. Okay, the reflection can be defined like this. Okay, this is actual reflection coefficients we call. Okay, reflection coefficients means the reflected power. Maybe most probably those are sometime measured in voltage, reflected voltage divided by the forward voltage. Okay, so this is the reflection coefficients. Okay, so that means some power will be reflected. Okay, some power will be reflected. So that is a problem. No, that means the wastage of the signal. Okay, if the signal is reflecting, that means some power will be lost. Signal power will be lost. Okay. So that is not good for communication. Okay. So what we need to do is we need to minimize this reflection. Okay. To minimize this reflection, we need impedance matching. Impedance matching. Impedance matching. So there are several impedance matching techniques. Okay, uh, you have already learned stub matching, and RLC matching. That is called lump element matching. Okay, and quarter wave transformers, quarter wave transformer. Okay. So these are some kind of matching techniques we have learned in microwave communication. Okay? So why we need matching? We need to minimize this reflection by matching these two impedance. Okay, that means we are going to equal this impedance. Okay, we are going to somehow equal this impedance. Actually not equal. Okay, not equal. Okay, we need to guarantee. We need to guarantee the maximum power transfer. Maximum power transfer. Maximum power transfer to the circuit, or component. That means the maximum power should be transferred from here to here. That means minimum reflection should be there. The minimum reflection should be there. Okay. So we need to guarantee the maximum power transfer to the circuits. Actually, that is the uh, requirement of the impedance matching to guarantee the maximum power transfer to the circuits. Okay, so actually maximum power transfer happens when the the input impedance. Okay, when if you match this input impedance, not input impedance. Okay, if you match this impedance to the conjugate of the input impedance. Okay, so in conjugate. Okay. So if you make the first impedance is equal to conjugate of the other impedance, okay, so that will guarantee the maximum power transfer. Okay, what is conjugate means? So you know that these impedance are complex impedance. Okay, so it has a real value and it has a imaginary value also. Okay, and this imaginary value can be a capacitive reactance or inductive reactance. It can be capacitive or inductive reactance. Okay. So if it is a capacitive, it will be minus, and inductive, it will be plus. Okay. So this, so most probably in antenna we have inductive reactance. So for antenna, most probably we have inductive reactance antenna. That means the input impedance, antenna input impedance is inductive normally. Okay. So we have R plus JXA type input impedance we have. Okay. So anyway, if the antenna input impedance is R plus JXA, okay, that is the input impedance of the antenna. Okay, we need to make this and this. We need to make this impedance to the conjugate of this input impedance. Conjugate means if it is plus, minus. If it is minus, plus. Okay, that means R minus JXA. Okay. So if you make conjugate, so this is called the actual conjugate matching. This is called conjugate matching. So this is it at conjugate matching, the power transfer is happening. Okay. So if I tell you the story again, okay. So when the signal is coming from one component to the other component, okay, if these two component impedance are mismatched, the signal can be reflected. Some part of signal can be reflected. Okay, but we need to minimize this reflection. For that one, we need to match this two impedance. One impedance should be matched to the conjugate of other. impedance. Okay. Then the maximum power transfer will be guaranteed to the circuits. Okay. So that is this term. Okay. Actually, that is one thing we need matching for antenna. Okay. To guarantee the maximum transfer, to guarantee the maximum uh, maximum power transfer, power transfer, to guarantee the maximum power transfer. Okay. And there is another uh, thing also related with antenna. Okay. So for example, if you consider the antenna in a Wi-Fi router, can you see? Okay. Can anyone tell me what is that antenna in our Wi-Fi router? Wi-Fi router, Wi-Fi router. We have antenna. Okay. What is the antenna in Wi-Fi router? What is the type of antenna in Wi-Fi router? What is the type of the antenna in Wi-Fi router?
Dipole antenna.
Sorry, what is the antenna?
Dipole.
Actually, how many poles are there? Actually, it is not a dipole antenna. It is only one pole is there. That is a monopole antenna. Okay. I am finding antenna. I have this antenna with me now. I'm trying to find one to show you. Okay. So in one Wi-Fi router, only one pole is there. Okay. So that is the monopole antenna actually. Not omni antenna. Okay. Omni antenna means I try to find antenna to show you, but I couldn't find. Okay, but anyway, uh, so it is like this. Okay, so it is just like aerial. No? Actually, it aerial. No? Okay. So only one pole is there. Only one pole is there. So it is like this. Okay. Actually, this is not antenna. Okay, this is a coaxial cable I take. Okay, so it is like this. Okay. Okay. So you have a conductor like this. Conductor like this. Okay. You have a conductor. Okay. And that conductor is connected to a connector like this. Okay. So this is a SMA connector, male SMA connector. Okay. So normally this connector has a 50 ohm impedance. Okay. This connector has a 50 ohm impedance. Okay. So once you design the antenna, okay, if you are using this connector, okay, if you are using this connector, when you are designing this antenna, okay, you have to uh, design the antenna input impedance should be equal to 50 ohms. Otherwise, you can't directly connect this connector to the antenna. Okay. When we are designing the antenna, we can design the antenna for any input impedance. Okay. To change the input impedance, we can match it. Okay. We can't design actually, we can match it. Okay. Somehow. Okay. So there are some techniques actually. Okay. So we will learn them. Okay. Uh, so this kind of thing is a monopole antenna, and maybe you can. I don't have to. Actually, I have several monopoles antenna. Okay, no, I don't have. They're not happening. Okay, so anyway, it is just like this. Okay, and you can change the length here. Okay, you can change the length. So maybe you know that in car, okay, you have the antenna, and also in radios, okay, you have antenna and you can change the length of the antenna. Okay, so we are changing the length of the antenna to tune the antenna for some design frequency. Okay, so this kind of one is a monopole antenna. Okay, normally for a monopole antenna, we select this length as lambda by 4. We call them quarter wave monopole antenna. Okay, we call them quarter wave monopole antenna. Okay, it is like this. Quarter wave monopole antenna. A quarter wave monopole antenna. It is like this. Okay, we have this kind of conductor, copper bar or something. Okay, and you can adjust that length. Okay, there is another copper bar like this and another copper bar like this. Then you can adjust the length. Okay, okay, and this is connected to the. So you can see that in this in this okay. So in this cable, you can see that, okay, in this cable, in this connector, uh, so this is SMA connector we call, okay. So you can see that there is a inner conductor, inner copper bar, that is yellow color one. Maybe you can see it, yellow color one. Here you can see it. There is a pin, okay, yellow pin, okay. And this is the outer, okay, this is the outer, okay. And this yellow pin is connected to the antenna, okay. connect to the antenna. Then this outer is the ground. This is the ground of the antenna. Okay. Okay. So this is connected to the pin of the connector, SMA connector, and that SMA connect. Then it is it is separated by a insulation. Maybe you can see that in white color. Okay, there is a white color insulation. Okay, and then the outer is connected. Outer again is connected like this. Outer is there. Like this. Okay. So this is the pin. Okay, this is the pin. This is the pin, and this is the outer. Okay. So actually, sometimes we make a copper plane like this. It is not touching to this antenna. Okay. Copper plate, that is the ground plate. That is working as a ground plate. Okay. So this kind of antenna is a monopole antenna, and length should be normally lambda by 4. It is quarter wave monopole antenna. Okay. So the length will be lambda by 4. Okay. Antenna length will be lambda by 4. Lambda is the design frequency wavelength. Okay. So this is the monopole antenna. Okay. And in Wi-Fi routers, we have monopole antennas. Okay. So what I want to tell you is that, okay, if you consider monopole antenna, as I told you, here we have the antenna. Okay. Then we have the ground plane like this. Okay. And this antenna and ground plane not touch. Okay. This is not touch. It is separated. Okay. Then antenna is connected to the inner pin of the coaxial cable, coaxial connector, okay, or SMA connector, SMA or BNC connector, okay, and this ground will be connected to the outer of the outer of the connector, outside of the connector, okay. Okay. So this bar is connected to this pin, okay, this pin, and ground. If so, consider that there is some ground plane, okay, just like it is a copper plate, okay, copper plate like this, okay, it is a copper plate like this, okay, like this, okay. So this is the ground plane. Then ground plane is connected to this outer this thread, outer thread of the connector. මේ outer එකට සම්බන්ධ කරලා තියෙනවා. Okay. So monopole antenna is like this. Okay. So if you want to connect our monopole antenna to a signal generator, okay. So maybe you have seen, okay, we have some signal generator in our labs. Okay. Have you seen our signal generator? Okay. So there are many signal generators in our lab. Okay. So maybe you can see that. Okay. Okay. So actually, those are this kind of signal generators are there. Okay. And we have port. We have output port. Okay. So we can get the signal from the signal generator. Okay. Maybe you can see that connector is somewhat bigger than this one. Okay. Somewhat bigger than this one. Okay. That connector is bigger than this SMA connector, okay? But the same construction. There is our middle conductor, then insulation material, okay, then outer conductor, okay, this outer conductor of the uh, connector, okay. So that is also, this is a coaxial connector. Actually, we use this connector for coaxial cable, okay. And this is also we used for coaxial cable. We call this BNC connectors, BNC connectors, okay. So BNC connectors, can you remember what is the impedance for a BNC connectors? In our oscilloscope also we have BNC connectors, no? In our oscilloscope also we have BNC connectors. What is the impedance of BNC connector? It can be 75 or more, 50 ohm. But SMA connector, this kind of connector, we have only 50 ohm. Okay. Try to keep remember this connector type. Okay. You should able to identify. Okay. This is actually another antenna connector. This type of antenna connectors are there in base station for 2G, 4G, 3G. This kind of antenna connectors we used. Okay. We used, and these are called N-type connectors, DIN-type connectors like this. Okay. Uh, so BNC connectors are there. Okay. So you know that. Okay. In BNC connector, this is the ground. This is the ground, and the middle one is the line. Middle one is the line. Okay. So you can directly connect this kind of antenna to this kind of signal generator. Okay. So actually, I have a signal generator here. Okay. So our normal signal generators are not in uh, radio frequency range. Okay. It is around maximum, I think, as I can remember, it is around 5 megahertz. Okay. 5 megahertz. Okay. 5 megahertz. Okay. Um, so this is not in radio frequency range. Okay. Around 50 megahertz upward, we consider that as radio frequency. Okay. So this is one signal generator we have. This is RF signal generator. Okay. This is RF signal generator. Okay. This RF signal generator. Okay. A small one. Okay. So this is working. Okay. So this is the RF output. Okay. This is the RF output. Okay. So you can see that it is also a SMA connector. Okay. It is also a SMA connector. Okay. And it is female type. It is not male, it is female type. Okay. So we can directly connect this male connector to this RF output like this. Okay. So you can connect it. Okay. So once you on this transmitter, if you on this transmitter, this antenna will be radiating the signal. Okay. Will be radiating the signal. Okay. So you can directly, without the issue, you can directly connect the signal generator to the antenna. Okay. Okay. So this antenna we can directly generate it. We can directly connect it to the signal generator, monopole antenna. Okay. And if we have patch antenna also has the same um, same structure. Okay. Patch antenna also has the same structure. Wait a minute. Actually, this is a patch antenna, okay? This is one patch antenna, okay? So this will be the feed line. This will be the feed line. And this is the antenna, okay? This is the antenna. And this feed line is designed to 50 ohm, okay? This feed line is designed to 50 ohm and input impedance also match to 50 ohm, okay? So here, maybe you can't see that, okay? So we will discuss about the patch antenna, okay, later. I hope, unfortunately, we don't have the patch antenna in our syllabus, okay? But definitely we have to, we have to discuss about the patch antenna because now most application use patch antenna, okay? So we will see uh, up to some level, okay? And also we try to design the patch antenna array also as our lab, okay? Using HFSS, we try to design, okay? So this is a patch antenna, okay? And this is the radiating element. This is the radiating element. This is a copper plate actually, copper. The coppers are painted here. And this ash color one is insulation. This is a insulator, okay? Then again, in this side, we have a copper, okay? Actually, this is a FR4 board, okay? This is FR4 board, okay? We used to construct microstrip and others, okay? This is actually microstrip, okay? This is a microstrip. Okay. So it is like this, okay? We have insulation material here, okay? And here we have copper coated plate, and here also we have a copper coated plates. These are copper, these are copper, okay? And this is insulation material, okay? So there are many type of this kind of microstrip boards are available, okay? FR4 and Neltec, Rogers likewise, okay? This FR4 is not good for high frequency, maybe a maximum up to 2 gigahertz, it is okay, okay? But these are high speed, these are called actually substrate, okay? These are called substrate, okay? So these are high speed substrate, okay? So it is like this, okay? So here we have a insulation material. Actually, that material is the FR4, okay? This material is called the FR4, okay? And that material, this insulation material is the FR4, okay? So it uses FR4 as the insulation material. So that is the substrate name also, that board name. The substrate means the insulation, okay? We called it substrate actually, okay? And okay, and this is the substrate or insulation material. We use FR4 here, okay? And this is a copper uh, coat, and this is another copper coat, okay? So this is called substrate material, okay? And there are many substrate material. This is FR4, okay? This is FR4 material. And there are others, Neltec, Rogers, likewise, used for high speed application. But FR4 is not good for high speed, okay? So up to 2 gigahertz, high speed means high frequency, sorry, not speed, okay? High frequency. This is not good for high frequency. The 2 gigahertz, up to 2 gigahertz, this will be okay. But for higher frequency, 30 gigahertz, likewise, we need to use Neltec or Rogers, okay? Okay, so what I want to tell you is that, okay, so this is the substrate, okay? So this is the substrate, okay? And we have constructed microstrip antenna on this substrate, okay? So this is the microstrip antenna, okay? And this is the radiating element. This will radiate the signal, and this is the this is the ground plane. This is the ground plane. So now if you want to connect a SMR connector, you can connect it very easily. How you can connect it? Okay. So there are SMR connect actually. Okay. We can directly fix to this board. Okay. Next week I will show you. Okay. So you can just solder that connector here, SMA connector here. Okay. This kind of connector. Okay. This kind of connector you can solve here. Okay. So this is the feed line. Okay. You can connect that feed line to the pin. Okay. This inner pin of the connector. Then for the ground, you can connect this outer part of the connector. Outer part of the connector is connected to the ground. The inner part is connected to this uh, feed line. Okay. Then this fetch also you can directly connect it to the signal generator if you have the SMA connector. So you need to have SMA male connector here. Then you can directly connect it to this signal generator. Okay, no problem. Okay, without any other component you can uh, connect. Okay, so the monopole antenna, patch antenna. Okay, and there are other types of antenna also. Okay, we can directly connect with the signal generator. Okay, okay, signal generator. Okay, but some antenna, for example, some type of antenna. Okay, for example, dipole antenna. If you consider dipole antenna, if you consider dipole antenna, okay, so it has two pole like this. It has two pole. This is one pole and this is another pole. Okay. So anyone can tell what is the ground of this antenna. What is the ground of this antenna? So if it is a monopole, it is like this. Okay. And if you connect, if you use use plate here, and if it is not connected, this is the line and this is the ground. Okay. Now tell me what is the antenna radiating element. This is the radiating element and this is the ground plane. Okay. So what is the radiating element here and what is the ground? So these both are radiating element. Okay. These both are radiating element. They both. So this is the antenna and it is radiating. So this one and this one is radiating. Okay. And there is no ground here. Okay. There is no ground here. So how you connect this kind of antenna to a signal generator? So you know that signal generator, okay, you know that signal generator has a ground and has a signal. Okay. Now, if you have this kind of one, okay, so one way is you can connect one pole to a signal and other pole to a ground, to the ground. Okay. Actually, if you have a line and ground, this is structure we called unbalanced. This is structure we called unbalanced. This is not balanced, unbalanced, because this voltage and this voltage are different. This voltage and this voltage are different. So we called it unbalanced. Okay, this is unbalanced. So normally, coaxial cable, if you consider coaxial cable, it has an outer shield and inner conductor. The outer shield, outer conductor, and the inner conductor are separated by a insulation material, insulator. Okay. And so when the signal is going, this is the ground and this is the signal. Okay. So this voltage and this voltage not equal. So we called it unbalanced structure. This is an unbalanced structure. Okay. So this coaxial cable is not a balanced structure, it is an unbalanced structure. But if you consider dipole antenna, actually it is a balanced structure because this is also radiating element, this is also radiating element. Okay. So these both are balanced structure. Okay. It doesn't has a ground. Okay, it doesn't has a ground. Okay, so now we have another problem. What is that? We have a balanced structure and we have to connect it to an unbalanced structure. Okay, so that means balance to an unbalanced system. Balance to unbalanced system. We have to connect. Okay, so this is also one matching. Okay, one matching. We called it balance to unbalanced matching. Okay, for that one, we are using the component as what is called balance. That is the balance. Okay, this is the balance. We use the balance to connect unbalanced structure to balanced structure. Okay, maybe now most probably you are using dialog TV or pure TV in your home. Okay, so actually the in dialog TV you are using parabolic antenna. Parabolic antenna. Okay, and there is a feeder like this. Okay, and this feeder is connected to the line. Okay, and this is a reflect, and also there is a ground also. Okay, that ground is also connected. Okay, so that is a coaxial cable, and the other end of the coaxial cable is equipped with the BNC connector. Okay, you can directly connect this BNC connector to your dialog decoder, dialog TV decoder, or satellite TV decoder. Okay, so this is a balanced structure. This is also a balanced structure. So you can connect, no problem. And it is, if it is pure TV, okay, actually the signals are not coming through the antenna. It is coming through optical fiber cable. Okay, so this so the optical connectivity directly come to this router. Okay, then from router to a decoder, then decoder to a TV, you can connect. Okay, so here also there is no any concern with balance to unbalance. Okay, but in television, maybe you can remember you are using two antenna like this, like this. Okay, and antenna cable is like this. Okay, so you are using two poles, actually two poles antenna. This is the aerial. Okay, this is the aerial, and this is actually a dipole. It's a dipole antenna because you have two poles. Okay, in TV and also radio set also sometimes this dipole antennas are there. Okay, so this is a dipole antenna. Okay, and television is not transmitter, it is a receiver. Okay, it is a receiver. Okay, the television is a receiver. Okay, now if you connect this signal to a receiver, okay, so it has in receiver it has a coaxial BNC output, BNC output, BNC connector, BNC connector in TV. Okay, so go and check. Okay, so the antenna port is still there. That is a BNC cable. Okay, actually that is a male BNC. I can't remember. Maybe female, maybe male. I'm not sure. Okay, no female. Like there is a female connector. Okay, in the TV, that is the ANT antenna connection. Okay, so that is a BNC connector. That means it's a balance structure, balance system. Okay, and this dipole is not a balance structure. It is a unbalanced structure. So actually we need to have a balance with, before the T between TV and this antenna. Okay, so maybe you can remember that. Okay, if you are still using antenna to see the television. Okay, let's say that balance. So can you remember that this kind of one is there? This kind of actually this is a balun. Okay, this is a balun. Okay, so these are the two antenna wires you can connect here. Two antenna wires, one antenna wire here and one dipole, one pole here and another pole here. So you can directly connect this to the TV. Okay, so in TV actually female BNC is there. So this will be the male. Okay. So maybe you can remember this gadget. Okay. So this is a balun actually. Okay, this is a balun. So this is a 75 ohm impedance is there. Okay, so it it allow to connect balance with the unbalanced structure. That is why we call this balance. Okay, so that is that. Okay, that is that. And I will go to that note. Okay, okay. So these are the matching techniques. I will upload this lecture once I get the approval. Okay. So now I think you know what is matching and you know how we can practically do the matching. Okay. Why we need matching. Okay. So so first we are using matching to match the impedance. Okay. So this is the antenna. Okay. So there is antenna impedance is in, and this is the transmission line, maybe the coaxial. Okay. Coaxial cable. Okay. The feeder. Okay. And if this one and this one not match, some power will be reflected from here. So we need to avoid this. So we need to have the impedance matching techniques here also. Okay. So you have learned these impedance matching techniques. Okay. Single stub matching, double stub matching, those things. Okay. So here I am not going to do this stub matching. Okay. So you need to have so you need to use the Smith chart to match using stub. Okay. So there are single stub, double stub, uh, open circuit, short circuit stub matchings are there. Okay. So you can use any techniques. Okay. Here. Okay. And also there are another technique also that is called T-match techniques. Okay. So this is the antenna. This is the antenna. Okay. And that antenna length is L and the diameter is the radius is A, diameter is 2A. Okay. So we are using this kind of structure. Okay. So here we use one copper cable with the diameter. That diameter is less than the antenna diameter. Okay. That diameter is A dash. A dash is less than A antenna diameter. And the length also less than the antenna length. You select this kind of one and you short this end and this end. Okay. And so this complete structure is the now antenna. This is the antenna. Okay. So the input impedance can be changed by changing these parameters. L dash, then this gap between the antenna and this structure. Okay, that is S, and the radius of this structure. Okay, so you can change the ZT. Okay, okay. And there is another one. Okay, another one that is also very interesting one. Okay, and this is a special type of T-match. Okay, so it is just use one wire. Okay, it use one wire like this, and Zin is directly related with the related, directly related with this cable impedance. Okay, this cable impedance, and it is 4 type. Okay, so by changing this cable impedance also you can change the cable impedance by changing the length, and also by changing the diameter. Okay, so you can change the input impedance as you wish. Okay, and there's another technique. Okay, so normally, so I told you that normally antenna, the input impedance of antenna is inductive. Okay, so this antenna, if this is a dipole antenna, it is inductive. Okay, so actually it is around 33.46.6 or something. Okay, I can't remember exactly. Okay, I will tell you. So this is the antenna, this antenna, and okay, and this antenna. Okay, now actually this whole structure is the antenna. Whole structure is the antenna because we use this T match here. We use this T match here. Okay, so here uh, this is somewhat like this Z in means the input here, input impedance here. Okay, so it will be yeah, no problem. Okay, you can do the do this one. Okay, uh, so actually this stub machine I will tell you. I will upload the material. Okay, so you can refer that one, but that stub machine will not come to the exam. Okay, because for the stub machine we need to use the Smith chart. Have you heard about the Smith chart? Have you heard about the Smith chart? Maybe in electromagnetism you are doing, no? Maybe in electromagnetism you have done, I'm not sure. Okay, but don't worry. Okay, so this is one matching techniques. Okay, so maybe something you couldn't understand here because we can't talk all the things related to matching. Okay, um, but I hope uh, in 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 electromagnetism these things are touching, as I know. Okay, but don't worry, you can follow this, and you can without a problem you can face to the exam. Okay, so so what are come for the exam I will deeply explain. Okay, so don't worry about that. Okay, and also I will give some question so you can also familiar with those. Okay, so don't worry. Okay, so so it is like this. Okay, so we are talking about this one. Okay, we are talking about this one. Okay, so this normally this is an in is inductive. Is an in is inductive. Okay, so this inductive. So here we have a inductive reactance. Inductive reactance. So it is like this. Okay. Okay. So if you consider this one, if you consider this one, it is like this. Okay. So you have a inductor like this. Okay, so this antenna is just like an inductor. Okay, like this. Okay, like this. So this is just like an inductor like this. Okay. So what is the reactance that is generated by this inductor? That is, if the inductance is L and the frequency is omega, that is J L omega. This is the inductance reactance created by this inductor. This is measured in ohm. Right? Make a, for a basic analog electronics, you learn this. Okay. So that is JL omega. Okay. And so it is like this. Okay. So here it is said that to eliminate the reactance of the antenna in self-resonant, to make the antenna self-resonant. What is self-resonant means? What is a resonant circuit? What is resonant? This one. Okay. Okay. Resonant means, okay. Resonant means, maybe you have learned this one also in electronics. Okay. Electrical, analog electronics. Okay. Resonant means if we have a conductor and capacitor like this. Okay. This is called series resonant actually. Okay. And if we are giving a signal to this. Okay. And what is the capacitance created by the inductor? That is, the reactance created by the inductor, that is JL omega. And what is the reactance created by the capacitor? Can anyone remember? We have learned this. What is the reactance created by the capacitor? What is that? That is 1 over C omega J. Okay, that is 1 over C omega J. Okay, then if you want to get up this J, you have to multiply this by J, and the denominator also you have to multiply. So this will be minus J over C omega. So this is the reactance created by the capacitance. We call this capacitive reactance and we call this inductive reactance. Okay. So what is the total impedance? Okay. So this is the resistance. Okay. This is some kind of resistance. Ohm. Okay. So this is serially connected resistors. These are two serially connected resistors. So if you want to find the total resistance, what is that? If this is R1 and if this is R2, the total resistance will be R1 plus R2. No? That is R1 plus R2. Okay. So now, so actually this is this is we called impedance. Okay. When we add this reactive, capacitive and inductive reactance, it will be an impedance. Okay. So what is the total impedance here? In the same way, you have to add this one to this one. So the total impedance will be JL omega minus JC omega. Okay. So you can see that in one frequency, maybe this one and this one will be equal. And then the impedance, total impedance will be 0. So JL omega will be equal to JC omega. Okay. Actually, this is we call the resonant frequency. That means at the resonant, the sum of inductive reactance and capacitive reactance are equal, and they will cancel out. Okay. And we have, if we have a resistor here, Okay. Only resistance impedance is there. Only resistant impedance is there. Okay, there is no any capacitive or inductive effect. Capacitive hari inductive effect hari නෑ resonant frequency එකේදී. තියෙනවා නම් තියෙන්නේ resistor effective එකක් විතරයි. Okay. That frequency we called the resonant frequency, and that is given as this J cancel out. Omega is equal to 1 over LC. Omega square, because this omega in omega is multiplied, that is omega square. So it will be 1 over LC. So omega is equal to 1 over LC square root. This is the resonant frequency. And what is self-resonant means? Self-resonant means at some frequency, again, this inductive and capacitive reactance will be same. Okay. But now, this has only inductive. This has only inductive reactance. Okay. To make this resonant at some frequency, what you have to do? You have to add the capacitive reactance also. Okay. And if you add it here also, that is also the same. Okay. So this will be, if you add some capacitor seriously with this inductor, any capacitor, any number of capacitor you can add seriously, then it can have a resonant frequency. Okay, that means at some frequency, this capacitive and inductive reactances will be same and cancel out. Okay, so that is we call the resonant. Okay, so actually now to make the self-resonant, you have to add the two capacitor along with the inductor. This is an inductive reactance, no inductive impedance is there. So you can add capacitive reactance. Okay. So that you can cancel this inductance by adding the capacitance. Okay. So capacitance can be calculated using these equations. Okay. So try to understand how this equation we derived. Okay. How this frequency we derived. Okay. And this C is the capacitance of the capacitor you are going to add it. Okay. And C is equal to 1 over 5F. This Xm is the inductive reactance. Okay. This Xm will be the inductive reactance and it will be the antenna reactance. Okay. So please try to understand this question by yourself. Okay. So if I give you a homework, so try to do it before the first class. Okay. Next class. Okay. If the antenna, okay, if the antenna, this is a homework. Okay. If the antenna reactance, if the antenna has a 6 nanohenry inductance. This nanohenry means the inductor. Okay, that is L, that is measured in Henry. Okay, and capacitor is measured in Farad. Okay, so if the antenna has 6 nanohenry inductance, okay, if the antenna has 6 nanohenry inductance, okay, what is the value of capacitor we need to use to cancel this 6 nanohenry, sorry, to cancel this inductive reactance effect. So that is a question. If the antenna has a 6 nanohenry inductance, what is the value of capacitor we need to add to cancel this inductive reactance effect of the antenna? Okay, so try to do this question. Okay, so this kind of question also will come to exam. So this kind of question will come to exam also. So try to solve this one. Okay. So it is very easy. Okay, it is very easy, and you no need to keep this equation in your mind. Okay, so if these equations are required, I can give it to you. Don't worry. Okay. So no need to keep remember this equation. What you need to do is you need to understand. And if I ask, you should be able to apply them to solve the problem. Okay. Okay. So we will stop. Okay. And next week we will try to complete the matching. Okay, matching parts. I hope we can complete it. No issue. Okay. So okay. So try to do that assignment. Okay. Don't take much time about on that. Okay. You spend much time on it for the calculation. Okay. For the simplification, don't take much time. Okay. If you can't simplify those equations, you can just avoid. You can just give up them. Okay. Okay. So we will stop. Do you have any question? If you have any question, you can ask me. Otherwise, you can leave. No problem. Okay.